So this is the third recording that we actually have. So what did we end up getting for the sums of squares of data set 5? That should be pretty simple. It's always 2. What did you get for the sums of squares for data set 6?
6.
You got the number of 6. So in terms of variability, data set 5 has the sums of squares of 2. Data set 6 has the sums of squares of 6. The question is there a problem with this? Does data set 6, when you eyeball it, really have more variability than data set 5? No. So this seems to be a problem. It seems, what's the case here? What is the problem? What happens to, when you have more in your sample, and you'll probably want to write this down, when you have more in your sample, it seems the sums of squares is just going to be naturally what? Higher. The value is going to be bigger and higher. So it seems there is a bias. You would call this a bias. There's a bias such that when you have a larger data set, the sums of squares is naturally just higher. The reason I chose these two data sets was because really they have the same kind of spread, don't they? But one data set just has more numbers. So the problem that we have here is that the variability really is about the same, but the sums of squares, when you have more numbers, is biased. That's what a statistician would actually use. They would use that word bias. So is there any way to fix this? It seems the sums of squares, the take-home message, the sums of squares are biased such that if you have different sample sizes, the one that has more in it is going to be larger. So it's biased. Is there a way to fix that? The next step would be to get the variance. And the idea, if you look at the formula on the screen, the way we get something called variance is we take the sums of squares and we divide that by what? Yeah, degrees of freedom, it says, but in this case, the simple way of saying that is n. What does n represent?
The number of patterns, like
the number in the sample. The other word that we use for variance, and you'll want to write this down. The other word we use for variance, it's often called the mean square. The mean sums of squares. It's often called the mean sums of squares. Because what are we actually doing with the sums of squares? We got the sums of squares, and what are we doing with them? Kind of getting an average. So you could call the other term for variance is called the mean square. Obviously, there are a bunch of bad jokes to make about mean squares, but I don't want to be a mean square and make one of those. So the other term for variance is a mean square. What do you get if you get the variance for data set 5? What is the variance for data set 5 then?
what would the DS be?
DF, it's called degrees of freedom, and all you need to know for degrees of freedom right now, if you're dealing with a sample, if you're dealing with a population as we are here, the degrees of freedom, I'll get into that in a little bit, but the degrees of freedom is simply the number in the population. So how many people do you have in the population?
Oh, never mind. I was reading the thing wrong.
No, I kind of put them next to each other because the more general way it's degrees of freedom, but that stands for the number in the population. It's going to be a little different a little later. So the degrees of freedom for for population data set 5 is what? How many are in that population for data set 5? 3. So what is the variance for data set 5?
1.67? 1.67?
No, I don't think so.
What is it?
It's 0.67, 2/3, right? It's 2 over 3. Ashton, are you seeing that or no?
Yeah, I wrote something wrong down.
So data set 5, the variance is 2/3. How about data set 6? You got 6 over what now? 6 over 9, which is also, is that a good thing? It should prove out to be a good thing. Because when we looked at these two things, the variance, it should be about the same because they really did have kind of the same spread. So the way we fix, if you have different sample sizes, which is better to use, the sums of squares or the variance? Variance is much better to use if you have different sample sizes because variance stands for the mean square. And in this particular situation, they are equal, they should be equal. Because they both take into account the sample sizes we're dealing with. Sorry, the population. I shouldn't say the word sample here. They take into account the population you're dealing with. What symbol would you use for variance? If you look in your book, in chapter 4, see if you can find a symbol for variance. Looks like on page 108, they kind of have it. Do they give us the term variance here? The symbol for variance. It looks like in version 9, it's on... It's on page 113. It's kind of a...
Is it the AO looking thing?
It's kind of a sigma squared. Can you see that on... No, that's not a sigma. I'm a terrible artist. Can you see it in formula? It looks like 4, 4. Are you seeing it in version 8 as well? Let me help you. There's the definition. In version 8... There it is. Well, it's that. It's on page... Yeah, 115. Let's see if it's there. Oh, there it is. It looks like it's on page 116. It's the sigma squared. Can you see it there? Ah, that's the symbol. That's what I'm trying to draw there. So the symbol for population variance is sigma squared. And notice that stands for the sum of the deviations, the average sum of squares. Is everybody still okay with me here? This will get a little more confusing, I think, in just a minute or so, but that's okay. Sorry about that. We're almost there. E. Notice what I put in E. Have people heard of the standard deviation before?
Yes.
The standard deviation is basically on average how far is a score going to be from the mean. The standard deviation is on average how far will a score be from the mean. What does it look like we do to get the standard deviation?
Square root.
You just take the square root of the variance. So I don't know if you have your calculators, but 0.67, the square root of that, that is the standard deviation. A lot of statisticians use the standard deviation.
And also, what will the score be from the mean?
Yeah, so if you were going to, what did you get? Actually, maybe somebody can do it on their calculator. What did you get for the square root of 2/3? Is it 0.81?
Oh, 0.82.
Okay. So we were close. So 0.82, what that basically says is if you're working with data set 1 or 2, if you randomly picked a score, how close would you be to the mean? You'd be like 0.82 from the number 3. So it's on average, how far away is a score going to be from the mean? So going back to the original question, and we're almost there with this particular part of the class, when we look at dispersion, that's kind of the take-home message. When we look at dispersion, there are 3 primary products that we look at to measure dispersion. The first one is what? Not the range, nope.
The sum of squares.
The sum of squares. So the first measure of dispersion that we consider useful is the sums of squares. What's the problem with the sums of squares? It's biased if you have
An outlier.
Different, not outliers, different sample sizes, But the sums of squares is often used, but if you have different sample sizes, it's biased. Better if you have different sample sizes is to use which one?
Variance.
The variance. The variance is also called the mean square because you basically take the sum of squares, you divide it by how many scores went into it. The other one that's most often used, if you just want to see on average how far will a score be from the mean, you use the standard deviation. Those, say again?
Real quickly, is the standard deviation always calculated the square of the variance?
Yeah, the square root of the variance, although in some situations you'll just get a standard deviation and it won't go through variance first. But yeah, it's the square root of the variance. Comments or questions? Okay, let's see what we've got next here.
I'm sorry, so those three are the things that you look for dispersion.
Yes. Those are going to be questions you're going to be asked probably on the take-home test. It looks like we've got an in-class problem for you folks to work on to make sure you get the idea behind this. And then we've got one more thing really to cover here, and then we're in good shape. Okay, so we've got an in-class problem. So let's see, in-class problem for population of 3. So now we're saying we have 3 people in the population for JMU and MBC. JMU, the 3 scores are 3, 5, and 7. MBC, the numbers are 1, 4, and 7. So 2 questions for you. Number 1, who has the better attitude? And which group has more dispersion in their data?
Does a higher score represent a better attitude?
Well, that's for you to figure out. That's why I posed the question. The answer to your question would, of course, be a yes, but I didn't want to say that until we were done with it. So take a few minutes, see if you can work on this. If you want to partner up with a friend, you can. If you want to work independently, you can. Ashton, you work alone.
Oh.
So we'll pick it back up in about 3 or 4 minutes here or whenever you get this work done.